Mr. GiGi. We've been talking about plane mirrors and curved. We know that a big DO equals a big DI. A small DO equals a small DI. But not with curved mirrors. Concave and convex mirrors create different sized images.
This is a concave mirror. The reflective side is on the inside of the curve. The focal point of the concave mirror is located halfway between the center of curvature and the mirror. Because of this, concave mirrors have positive focal lengths. If you place an object outside of the focal length, you'll see a real and inverted image. This image can be projected. This image gets smaller as the object moves away. The object and image are the same size when the object is at the center of curvature. If you place an object inside the focal point, you'll see a virtual upright image that is always larger than the object. If you place an object at the focal point, the image disappears completely. This all occurs because light reflects off a concave mirror and converges or comes together at the positive focal point. This is a convex mirror. The reflective side is on the outside of the curve. The focal point of the convex mirror is located halfway between the center of curvature and the mirror. Because of this, convex mirrors have negative focal lengths behind the mirror. No matter where you place an object in front of a convex mirror, you will always create a virtual upright image. The further the object, the smaller the image. This all happens because light diverges or spreads apart based on the focal point as it reflects off a convex mirror.
This is a concave fire starter. It uses the sun's radiant energy to light a piece of kindling right here at the focal point.
Light enters the fire starter as parallel rays, but always reflects straight through the focal. This concentrates or focuses the light at the end of the fork.
Let's go set something on fire. Thanks for stopping by. Remember to like and subscribe and wash your hands.
Hello and welcome back to my podcast. I know more about movies than you do. Don't forget to like and subscribe. Today we're going to be looking at clips from the classic Cool Hand Luke, featuring star of Salad and Screen, Paul Newman.
In the movie, this guard's famous glasses are convex. They reflect light to create virtual, upright images of the inmates. The further the prisoner is away from the guard, the smaller the image is.
The director uses convex mirrors as a visual cue to explain how the guard sees the prisoners.
In the clip, the guard's convex glasses had a focal point of 20 centimeters. Because they're convex, it's negative 20 centimeters. The prisoner is 170 centimeters tall and 100 centimeters away, so the DO is 100 HO is 170, and we're looking for DI, the distance of the image. I know DO, I know F, I want die. That height of the object is going to be for the next part of the question. Substitute in what you know. Remember to use the inverse button, and remember to use the negative for the focal point. Now we can solve for 1 over die. To get die, or DI, the distance of the image by itself, we take the inverse using our inverse key. A negative DI means that we have a virtual image. It's an image behind the mirror. We can use all of this given information to find the height of the image. Because I know die do, I know HO, and I want HI, I can use that relationship. Remember, the negative in negative DI is not the same as negative 16.67. So I take the negative of negative, which is a positive. Cross multiply, divide both sides, and there is my HI. Because it's positive, it is a positive height, an upright image.
The prisoners not only appear as virtual, upright images to the guard, they also seem to be smaller. The images have a smaller height. He sees them as less than him. Thank you very much for joining me live from my parents' basement. This has been I Know More About Movies Than You Do. Hello and welcome back to Making It Up, the makeup tutorial show where I have no idea what I'm doing. Today we're going to be using some makeup and a makeup brush. But most importantly, we'll be using this concave mirror. Now, right now, this concave mirror is creating a real inverted image in my eye. It's not very helpful to have an upside down image. So I need to move closer. As I move closer, I hit the focal point and my image disappears. I can't see myself in the mirror anymore. As I move even closer inside that focal point, I can start to see that I've created a virtual upright image. So now if I wanted to do some eye makeup, I can see myself with a bigger image. I'm almost zoomed in. Well, now let's make ourselves pretty. Ow.
Your face is 40 centimeters from a makeup mirror that has a center of curvature of 50 centimeters. We want to start by finding the focal length. We know center of curvature is 50 centimeters. We know the distance of the object is 40, and we want to know the focal length. The focal length is equal to half the center of curvature. So the focal length is 25 centimeters. It's positive, so that means this is a concave mirror. That focal point is helpful in our ray diagrams, but it helps us calculate the image's location, or the d sub I. We know the focal point, we know the distance of the object, and we want the distance of the image. There's our formula. Substitute in what you know. You can either bring over that fraction by subtracting the 1 over 40, or use your inverse button in your calculator to make some decimals. Either way, you're going to get 1 over die, so the last step is to take the inverse. This positive DI, positive distance to my image from the mirror, means that I have a real image. And that's because this concave mirror has an object placed outside of its focal point. If we move the object inside of the focal point, we have some different information. Focal point stays the same, the height of the object stays the same, but now our d sub O, our distance from between the object to the mirror, is only 10 centimeters. It's less than our focal point of 25. So now we're expecting a virtual image. So we're predicting a negative DI. Substitute in what you know, solve for what you don't. Remember to use that inverse button. You're going to end up with 1 over DI, 1 over the distance to the image, which gives us the DI of negative 16.67. Negative because it's a virtual image behind the mirror. Once we have all this information, we can find the height of the image, or the h sub I. Now, the d sub I, the distance of the image, is negative, so we expect the opposite. We expect a positive h sub I. There's hi-ho, negative di-do. Plug in what you know, solve for what you don't. Remember, the negative in the formula is not the same as the negative in negative 16.67. That gives us a positive answer when we cross multiply, solve for h sub I, and we end up with 50 centimeters. It's positive as expected, which means it's upright. If you want to find the magnification between an object and its image, you just need to compare the ratio between the object and the image's heights and distances. We have both. So we can use the full formula and check it
both ways. I'm going to look at the heights and the distances. When I look at the heights, I get 50 divided by 30. When I look at the distances, again, negative, that's positive 16.67 divided by 10. Either way, it comes out to be about 1.67 or 1.67 times bigger. If that value was negative, it would mean our image is inverted or upside down. If that value was less than 0, it means that our image is smaller than the object. But because it's bigger than 1, it's larger, and because it's positive, it was upright.
Now see, with the right focal point and enough practice, you too can look beautiful.